Hello, thank you for watching this presentation. My name is Manar Samad, and on behalf of our team, including Maxims and Furkan, I would like to present this paper, Mining Social Media Data to Predict COVID-19 Case Counts. Now, we all know the numbers and what the devastation this pandemic has caused to human civilization. One of the questions and issues that is puzzling the policymakers and researchers is the uncertainty and unpredictability surrounding this pandemic. We wish we could predict the outbreak at different geographic locations on time so that we can put some preventing measures, including border closures, self-quarantine, mask and vaccination mandates in place. Now, before CDC and the government gets to know about the outbreak and about a potential progression of a pandemic so that they can post some public safety guideline, it can be too late to escape hospitalization, illness, and death. So the question is, how can we obtain the intelligence about potential outbreak of this pandemic for different geographic location? It turns out that social media is a platform where humans are pouring massive amount of data on daily basis, on hourly basis, that has the potential to provide us some useful information, real-time information on any social economic trends. So if we look at the literature, there are a lot of papers on COVID-19, and if you mainly focus on social media studies for COVID-19, you will see invariably all the papers are trying to correlate two things. The one thing is the number of posts on social media. They're trying to correlate with the number of COVID-19 case counts. But in this particular paper, we'll be trying to do something more sophisticated. We know that the social media text has some semantics that we can derive using natural language processing algorithms. The question is how we can correlate those semantics from the text with the actual COVID-19 case count so that we can better predict from the actual social media data. Now, in fact, you will find social media research is introduced to public health research. You see this circle on the right-hand side, social media used for surveillance monitoring, social media for infodemics, which is the measure to prevent the spread of misinformation, and social media as disease control. Also, social media is useful to detect mental health issues at population level, but in this particular research, we'll be mainly focusing on using social media as a tool for surveillance monitoring. Now, in order for us to accomplish this research, we want to do some data collection. For this reason, we picked up Twitter as a social media platform. We used the Twitter API 1.1. And what we did is we used these two keywords to collect tweets originating from 50 different cities in the United States. So we started collecting on March 14, 2020, which was the kind of the official day when the lockdown started all over the world, till August 23rd, 2020. And our target variable was the positive COVID-19 case counts for different cities at different time or dates that we collected from the Johns Hopkins Public University Public repository and dashboard. So as you can see on the right-hand side, the Twitter data set is fairly complicated. We have tweets for individual dates. Each day has 50 different cities, and for each city we have hundreds of tweets related to COVID-19, and each tweet is a document, unstructured document with its own text and metadata. So we had to process all these things to be able to accomplish what the goal of this project. Now, as we know that machine learning models cannot digest text, it needs to be converted into some numeric representation that we call the text embedding. For that reason, we use these 6 NLP algorithms that converts the text into semantically meaningful numeric vectors for machine learning and other processing as needed. So as you can understand, we have 3 data dimensionality. We have data across cities, dates, and tweets. So for word embedding, we converted individual words into a semantically meaningful word vector, and then we aggregated these words within a tweet to create something that we call the tweet embedding. And then we aggregated all the tweet embeddings coming from an individual city on a particular date to represent something that we call city embedding. And that city embedding, that vector representation representing the COVID-19 tweets from one city on a particular day was used to predict the COVID-19 case counts later on. Now, as you know, the target variable was the COVID-19 and the city embedding was the word vector. And it turns out that this whole data problem is a time series prediction using text embedding. So we consider that the time series is starting from day 1 and day 14. We can split this time series, as you can see here, into time series samples. So each sample can have 4 time steps, and each time step or each day can be represented by city embedding, as you can see over here. So in that way, we can break down a long time series into samples of n time steps. And as well as we can use that time series to be able to predict the COVID-19 case counts, let's say m days in the future. Because this is a kind of a time series prediction problem, we use the Lstm network. So Lstm is a kind of neural network which stands for long short-term memory, and it has 4 different gates, as you can see here. The good thing about Lstm that it can capture both the long-term dependency and the short-term dependency into the future learning. ST stands for the long-term dependency, and with the short-term dependency, we get the H2 representation, which is kind of an aggregate representation of the entire time series data. And next to this HT, we couple a dense layer that maps the HT with the actual COVID-19 case count, which is the YT. So in that way, we're using a time series regression model to be able to predict or estimate the COVID-19 case counts from the city embedding vector. In short. So for model evaluation, because this is a regression problem, we use R-squared score and normalized root mean square scores. And we did quite a few of experimentations. The first one is we compared the state-of-the-art NLP text encoder for this particular problem. We studied the effects of varying number of time steps and the days in the future that we want to predict. And we also reproduced the results for 8 representative cities in the United States. Now, the first thing we need to understand is tweets can be very messy. It can come with a lot of undesired characters, keywords, and URLs, hashtags, and so on. So we had to get rid of all those undesired entities. And then we tokenized the tweets so that each token or each word can be represented into some sort of word embedding. So this was the pre-processing step. And then the next step is we had to model the time series prediction. So the way we did that on the right-hand side, you can see that, let's say city embedding is coming from day 1 and the Lstm is trying to predict the COVID-19 case count on day 4. In that way, in this particular scenario, we are trying to predict the COVID-19 cases 3 days in the future. So we have the number of time steps per sample, which is the length of our time series, and we have the number of days that we consider to predict the case counts in the future. And we have these 8 representative cities in the United States, starting from southeast, we have Miami, to all the way in northwest, you have Seattle. And at the same time, we had to make sure that the test time series data that we have, under no circumstances that time series data have any overlap with the time series that we are using for the training data. In that way, we avoid any type of information leak during our predictive modeling. So the first thing we did is we compared those 6 NLP encoder. In this particular case experiment, what we did is we used time series of 9 time step samples, and we predicted the COVID-19 case count 6 days in the future. And what we found that the universal sentence encoder outperforms the other 5 models in 6 out of 8 cities. And that's why we picked up universal sentence encoder in our subsequent experiments and result reporting. And then here on the left-hand side, you see the normalized root mean square error and the square error score. And the x-axis, you have the number of time steps per sample, and the y-axis is the number of days in the future we're considering. So a couple of quick observations that when we are predicting case counts 3 days in the future using 6 time steps, apparently it's giving us the lowest root mean square error, and predicting 5 days in the future using the same 6 time step sample gave us the highest or the best R-squared score. And invariably what we have found that the representation with the 9 time steps contains the most information, because the R-squared score is found to be always greater than 0.8. In these two tables, we're showing the effect of the number of days in the future we're considering for different cities. Invariably, we see that the R-squared scores are greater than 0.7, so they're kind of highly correlated. It shows a strong correlation for 9 time steps per sample. And the best prediction of daily case counts, we have found that most of the times 6 days, predicting 6 days in the future and 7 days in the future were giving us the best results across most of these cities. So this is a visualization of the actual case count and the predictive case count for 8 different cities. As you can see, these are quite correlated. And in this particular case, we use the test time series data with 14 samples, and we're using 9 time steps per time series to be able to predict the case count 6 days in the future. And overall, we see quite a few correlated trends, although the general trend was upward. But in general, most of the cases, they followed the trend to give us some interesting results. So in conclusion, the time series social media text is predictive of COVID-19 case count using NLP encoders and recurrent neural network. We found that the universal sentence encoder is the best model out of 6 different NLP models in this particular case, and the universal sentence encoder obtains the best normalized root mean square error. And we also found strong correlation between the actual and predicted daily case counts. And considering 9-day time sample, the R-squared score was always over 0.8. So in the future, impact of sample size, text processing, and encoding will be studied. And we will be creating a joint embedding learning that not only obtains the text embedding, it also performs the prediction within the same time frame, within the same computational framework. And we should be able to explain model performance to mitigate any anomaly. These are some of the references, and thank you for your attention.